Hi everyone, my name is Nachiket, and along with my teammates Manjot and Bashar, we developed the RogueWave coffee automation system for our ECE 492 capstone design project. We partnered with our sponsor, David from RogueWave Coffee Company, and under the technical guidance of Professor Stephen and Felipe, a master student candidate, we were effectively able to develop a working prototype. Our project addresses a key challenge in commercial coffee roasting, achieving consistent and repeatable roast quality. We combined real-time sensor technology with advanced machine learning algorithms to generate automatic roast parameter recommendations, greatly enhancing roast consistency, repeatability, and operator efficiency. We developed a responsive web dashboard that integrates seamlessly with sensors to provide operators with live roasting data, recommendations from our machine learning model, and progress tracking. The system also enables session logging and easy switching between different predictive models, helping operators fine-tune roasting parameters effectively. Testing in simulated environments showed excellent results. Our LSTM-based machine learning model accurately tracked roast conditions and provided real-time parameter adjustments, demonstrating robust performance and readiness for real-world applications. Overall, our prototype successfully showcases how data-driven automation can revolutionize coffee roasting operations. We're excited about the future possibilities, including integrating anomaly detection, advanced calibration, and real-time API syncing for enhanced workflow integration.
Here we have the essential hardware for our coffee roasting automation system. At the center of it all is the Raspberry Pi 5, which handles our data collection, machine learning processing, and overall system control. On top of the Raspberry Pi 5, there is an AI Top Hat module. It provides additional machine learning acceleration for real-time recommendations. And on the bottom left, we can see a small board that is a BME 688 sensor that can measure ambient temperature, humidity, uh, pressure, and gas composition. This single sensor can be daisy chained with more sensors for scalability, so we can monitor multiple environmental parameters as needed. For connectivity, the system supports both Ethernet and Wi-Fi, letting the user access it via SSH or direct monitor and keyboard setup, whatever works best for the user. This flexibility makes the setup both powerful and easy to integrate into different roasting environments. Now I will be demoing the system in action during a roast session. This is how our user interface looks like. First, I will be selecting the model A, which only takes the bean temperature as a parameter, and then I'll click start on the roast. And on the left side, we can see the live graph displaying the internal bean temperature inside the roaster. And on the right side, we can see the graph that shows the predicted gas settings generated by our LSTM regression model. At the very beginning of the session, the operator preheats the roaster to a target temperature and then starts pouring the coffee beans slowly into the drum. And that's why at the beginning of the temperature graph, we can see a drop in temperature slowly. Now, skipping ahead a bit, the roast itself lasts about 15 minutes. During this process, the system continuously monitors the temperature. The recommendation engine adjusts the gas setting dynamically. It suggests increasing the gas flow when the beans haven't yet reached the target temperature and then lowers the gas as the beans heat up. This real-time feedback helps ensure a smooth, consistent roast cycle. Skipping ahead to the end of the session, we can see how the overall graphs start to take shape. The bean's temperature keeps going up until it hit that threshold, and as a result, the gas settings start dropping down. And then once we reach the end of the roast, a save button will become active, and the operator can choose to save this roast. And that will generate a CSV file that will contain all the parameters captured by our device during the roasting session. And also, the UI provides a live data summary on the top to make it easier for the operator to see the predicted gas setting instead of looking at the graph at any point in time. Now let's switch over to Model B. With this model selected, we can notice that there are 3 extra graphs appearing at the bottom of the dashboard. These graphs display the ambient conditions, specifically temperature, humidity, and pressure. These additional parameters are included as inputs for the prediction model to improve its accuracy in real-world conditions. While this run demonstrates the system's capability using these extra inputs, it also highlights our forward-thinking design. We've built the system to be compatible with adding more advanced models in the future once we have a larger dataset of ambient roast conditions for training. And as the session goes by, the graphs take a similar shape. The model predicts to increase the gas setting to increase the temperature of the beans, and when it hits that target temperature, the model will suggest for the operator to drop the gas setting in order to maintain that bean temperature until the roast is done. And similarly to Model A, we have the option to save the roast in here as well. To wrap up the demo, I will just go over a brief review of the roast logs saved as a CSV file. Regardless of whether we use Model A or Model B, the system captures all the essential parameters. Our logs include both the internal bean temperature and the ambient conditions. In this preview of the roast that we saved earlier, we can see that for the first few entries, the predicted gas column is empty. This is because our LSTM model relies on rolling window of data before it can generate its first prediction. Once enough data is gathered, the model starts populating the predicted gas settings. This comprehensive log is crucial because even when Model A is used for real-time recommendations, we still capture ambient data for each roast. Later, these records will be invaluable for training a more sophisticated model, such as Model B, which incorporates all these parameters to enhance production accuracy.
To begin with, we'll highlight some of the key successes we had throughout the project. First and foremost, our real-time data acquisition system met expectations. We successfully achieved a 1 Hz polling for all sensors, which included the ambient environmental variables. This data was continuously logged without packet loss or lag, providing a reliable stream of time series data to drive both the machine learning model and our dashboard interface. Secondly, the performance of our machine learning system was strong. After exploring various models, we implemented an LSTM regression model that could generate gas setting recommendations within 3 to 4 seconds of new input data. This met our latency goal and demonstrated that real-time on-the-edge inference is possible even on resource-constrained hardware. Our hardware integration also proved robust. We deployed the system on a Raspberry Pi 5 with an attached AI accelerator. This allowed us to perform both real-time data processing and machine learning inference directly on the device without the need for external computation or cloud services. Finally, we designed a web-based dashboard to present sensor data and model recommendations in real time. The UI is accessible from any browser and updates automatically, giving roast operators a clear view of roasting conditions and model outputs during a session. This dashboard also includes tools for model selection and roast session review, making it a key part of the operator workflow. Of course, as with any engineering project, not everything went exactly to plan. One of the key issues we encountered was the incomplete mechanical integration of the enclosure itself. While we selected an IP65 rated junction box to prevent the electronics from dust and heat, we didn't have enough time to fully implement cable routing, panel mounting, and sealing. As a result, the current setup is not ready for deployment in a high temperature commercial roasting environment, although the enclosure is in place and partially functional. Another limitation lies in the current machine learning model inputs. At this stage, the LSTM model uses only internal beam temperature data to make recommendations. While we did successfully log ambient temperature, humidity, and gas concentration data, those signals are not yet integrated into the real-time prediction pipeline. This limits the model's ability to respond to environmental factors that may affect roast behavior. Finally, we face limitations with our sensor calibration process. Right now, calibration is static and performed manually, often using Cropster as a reference. There is no built-in mechanism to detect drift or prompt recalibration, which could lead to accuracy issues over longer periods or when changing sensor configurations. Dynamic calibration remains an important target for future development. Looking ahead, there are several improvements that we recommend for future development to enhance the performance, reliability, and usability of the system. One key recommendation is the implementation of anomaly detection and predictive maintenance. By analyzing historical trends in sensor data, the system could be extended to detect gradual sensor degradation, abnormal roast conditions, or faulty hardware before these issues lead to quality loss. This would improve both consistency and operational reliability in real-world settings. Another important area is the enhancement of the machine learning model. During this project, the model was limited to internal beam temperature as its sole input, as future iterations should incorporate ambient sensor readings such as temperature, humidity, gas levels, as well as derived metrics like rate of rise. These inputs would enable more accurate and phase-specific recommendations, particularly during key transitions such as drying and first crack. We recommend implementing dynamic calibration profiles. Rather than relying on single static calibration, the system could allow operators to select from profiles based on beam type, season, or location. Automatic drift detection could further prompt recalibration as needed, reducing maintenance burden while improving long-term data accuracy. Integration with Cropster is another logical next step. Many specialty roasters already use Cropster for roast logging and quality control. By syncing roast profiles and sensor data through Cropster's API, the system could offer a smoother and more familiar workflow, increasing its adoption potential. Lastly, we recommend completing the ruggedization of the enclosure and further enhancing the dashboard visualizations. The enclosure should be fully sealed and mounted for safe use in high heat, dusty environments. On the software side, improved UI elements such as roast phase indicators and intuitive trend graphs could make the system more operator friendly and reduce training time. These future directions, if pursued, would help transition this project from a functional prototype into a robust, field deployable automation tool for data-driven coffee roasting.
To conclude, our project successfully demonstrated a proof of concept, delivering robust real-time recommendations and reliable data logging. With a modular and scalable design, we built an architecture ready for future potential, although no further development is currently planned. Throughout the process, we gained valuable experience in sensor integration, machine learning control, and real-time automation, setting a strong foundation for future initiatives in data-driven automation.